we shall go through a lecture, which is not always covered. So, but I believe we have time, and this is an important topic. So we are coming back to solution of systems of nonlinear equations. So as you remember, before we were considering equations like that, but they were scalar. So what does it mean? It means that f is a function which returns a scalar value with just, let's say, a real number, and x is a scalar, just a scalar, which means just a real number. So we are limiting ourselves by real numbers, although some of the methods can work also in complex plane. Okay, so we were solving these type of the equations using several methods. So the first one was bisection. Second was fixed point iterations. And third was Newton's iterations. And each method had its own positive and negative sides. So, for example, bisection is pretty robust. From the other point of view, it's not as fast as Newton's iterations and is a little bit more complex to implement than fixed point iterations. So fixed point iterations are easy to implement, but the problem is the convergence. So if you remember, for fixed point iterations, we had this contraction map theorem saying that at the root, this has to be less than 1, the magnitude of the derivative of our function f. The only problem is that for fixed point iterations, okay, I will call it f tilde. So we had this type of the equation. So we were requiring that the derivative, magnitude of the derivative is less than 1, and then we know that if we start close enough to the root r, so we will be able to converge. So, but the thing is that this is pretty strict requirement. So even if it's not satisfied, we still can converge. So at least it happens so. Or there is no real explanation. What does it mean if we start close enough? So we know that if we start very close, I mean, as close as we like, so there will be the vicinity of the root in which we will have convergence. But the thing is that this contraction mapping theorem doesn't tell us about how close we should start. Okay, and Newton's iterations, it's a good method. It has quadratic convergence, right, with respect to bisection and fixed point iterations. So everything looks good. The only problem is that, as you remember, we had this. Okay. So we need to know not only the function itself, but also we need to know the derivative of the function. And the problem is that, for example, if your function is something like that, f of x is, let's say, integral from a to x of function g of x dx, g of y dy, right? Something like that. So this is relatively easy to compute the derivative. But if you, for example, have something like and here you have y and x is a parameter. So not always you can compute this derivative of that expression analytically. And then if you don't have analytic derivative, so what would you do in this case? And we had several approaches, like, so we went through several approaches which allows us to have a workaround. So for example, we were replacing f prime at xn with, so you remember that by definition, this is nothing else but this, right? And we were approximating it, saying that, okay, if we have convergence, right? So we can try to approximate. So if we have these iterations, results of iterations, which are pretty close. So what we can do, we can just try to use this is so-called secant method. So we can try to approximate this derivative using the values of the function at which we computed anyway here for the numerator on the previous steps. So, okay, so and what you can see here, we are using some numerical approximation of the derivative. You see, it's approximate equality. Okay, now let us have a look at the general case. So, like, for example, if you consider these, right? So this is scalar equation. Linear. And you can, you know that it's easily solvable if a is not equal to 0. Then x is b multiplied by a to the -1, or the same as b divided by 8, right? So now we already know, because we studied linear solution of systems of linear equations, that we can have this. So this is n by n matrix. This is n by 1 vector, column vector, and this is n by 1 column vector. And then we already know using that we can do LU factorization and find x, at least in some cases, as A inverse B, but really instead of computing A inverse, we just solve, we perform LU factorization and just solve using forward and backward substitution this system of linear equations. So it's more beneficial because LU factorization is 2/3 n cubed, and then you just the other contributions are proportional to n squared only. So the thing is that for finding A inverse, you need to do LU factorization and then extra operations on the previous matrix A in order to get to get inverse matrix, so it's just more costly, usually in the general case. So this is why. So you can formulate a solution of this equation in this form as A inverse multiplied on the right hand side. So pay attention, it's very similar to this, right? So just here we have A to the -1 power. So A inverse is essentially like a replacement of division by the matrix, right? So because we don't have division by the matrix, but we can introduce inverse matrix operation. Okay, so we know how to solve these, right? So we have methods of solution of systems of linear equations, but obviously we can try to generalize this original equation f of x equals to 0 into something different. For example, so we had f of x equals to 0, and now we can replace it with f vector function of x, which is also vector function, equals to the 0 vector. So, and we will be considering only the case of n entries here, n entries here, and correspondingly, in order to have equality, n entries here as well. So what does it mean? It means that our vector x is nothing else but x1, x2, xn, column vector with n entries, or you could say that this is n-dimensional vector in the Euclidean space. And f of x, by definition, is nothing else but f1 of x1, x2, xn, f2 of x1, x2, xn, and so on till fn of x1, x2, xn. Just this. So the result, you can, in general, write this compact form of a nonlinear system of nonlinear equations in this form, so that f1, x1, x2, xn equals to 0, then f2, x1, x2, xn equals to 0, and so on, to fn, x1, x2, xn equals to 0. So, and I'm writing this curly bracket to show that we are considering these equations together. So this is a system of nonlinear equations. Okay, so example. For example, like that. I'm just writing some crazy functions, so not particularly interesting for any practical application. And for example, like that. So, and then system of linear equations will be this. And we want to try x1, x2, x3, or we can say that we want to find the vector x such that it has 3 components, x1, x2, x3, which if we satisfy here, if we substitute in this system of linear equations, will satisfy these all these 3 equations simultaneously, right? So very similar to linear equations. The only problem is that instead of linear equation, simple linear equation, here we have some nonlinear functions in general. Okay, so so this is, we can call this system 3 by 3. So meaning that 3 by 3 system, although we don't have any matrices here, right? So saying that we have 3 unknowns and 3 equations. So as I said, we will be considering here only n by n systems, where the number of unknowns and number of equations is the same. Okay. Okay. So now let us consider. Let us try to apply the methods which we know already to this problem. Okay, so the easiest method to generalize is fixed point iteration. So let me remind you what we had. We had, so for example, from f of x equals to 0, right? We could go to the f of x plus x equals to x, something like that, right? And we could say that this is f tilde of x, right? And just to consider f tilde of x equals to x, problem like that. And then we were saying that, okay, xn plus 1 equals to f prime of xn. Idea was that at the so-called fixed point, so at the solution, right? Because left-hand side is equal to the right-hand side, so we will have equality, right? Because we know that root equals to this, right? So the result, we just saying that, okay, let us suppose that we have, if we substitute here our initial guess, then every next guess will be better, closer to the root. So, and then we gave this contraction mapping theorem, so which said that if this is less than 1 and we start close enough, then we have convergence. Of iterations to the root, right? Okay, so what we can do here, we can, of course, just instead of considering this f x equals to 0 vector, we can say that we will consider some f tilde of x equals to x, something like that, right? So just replacing here. So idea is exactly the same. We can add the x vector, right, and so on. So again, we are getting something very similar to what we had in scalar case, right? And then we can formulate fixed point iterations in the following way. And there is a generalization of contraction mapping theorem for systems. Which says the following, that we require some essentially we require some determinant of some matrix which is analog of the derivative of our function here. Oh yeah, sorry, and nobody corrected me. So of course there is a derivative here. So so we can try to introduce the analog of contraction mapping theorem, so which will be just essentially that some matrix which we will denote d of f. Okay, f tilde. So that its determinant would be less than 1. Okay, so I will introduce the analog of the derivative for the function. So it's denoted, can be denoted differently, like that, like that. And this is the following. This is n by n matrix. And in which, in each entry of this matrix, we have a partial derivative of the corresponding components. So just remember that f has these components, right? f1, f2, fn, right? And they depend on x1, x2, and so on till xn here, for example. So this analog of the derivative will be Jacobian matrix. Oops. And second row is just the same, almost. So essentially here, df I jth element is nothing else but df I by dxj. So this is called Jacobian matrix. And of course, you can compute it in every point. So, and condition is that determinant of the Jacobian matrix at the root has to be strictly less than 1, approximately. So it's a little bit. It has some extra conditions on the function, but I don't want to go there. So because we will not be using, we will not be considering fixed point iterations here. But what is good about fixed point iterations? Generalization is straightforward. So if here you represented your equation in this form, as in this form, and then you just written fixed point iterations like that, right? You just said that, okay, these, let us suppose that this will be better approximation, and then you are just you can easily compute your next approximation, knowing the function and the previous approximation. Okay, now here, so you formulate your equation in very similar form, just vector form, and then use the same, exactly the same approach to formulate the iteration process. You are saying that, okay, I suppose that this iteration process converges, and then it's easy to compute the next iteration, this one, using just value of your function. So evaluation of your function, yeah, by the way, vector function, just computing it from the previous iteration. Okay, so condition is, again, relatively, I mean, we have the condition of convergence. The only problem with this condition is the following, that to compute this Jacobian is not that easy. And again, in order to use the condition, it's not very practical, because you need to know the root, right? So because this condition, so you need to evaluate it at the root. So this Jacobian, exactly like what we had here. So you need to evaluate it at the root. So it's not very practical, because usually you don't know the root. Okay, and if at least here you could plot it, right? And see if the slope is less than 1 by the magnitude in the vicinity of the root, which you can see by your eyes, then here in n-dimensional space, of course, it's impossible. It's not very practical. So, okay, let me just write that. Okay, dfk by dxj here is dfk by dxj computed at the corresponding coordinates. Okay, so let me also remind you what this means. The partial derivative. Partial derivative is the derivative of a multivariable function. So just remember that we have x1, x2, xn, right? When I compute, for example, derivative with respect to dx2, I consider all other variables frozen, like constants, and compute derivative only with respect to the corresponding, for example, x2 here, right? Or if I need to compute with respect to x3, so I'm considering all variables frozen, like constants, and just compute the derivative only with respect to x3, and so on. So this is what is called partial derivative, which is different from full, because we are considering, we essentially like freezing all the variables and changing just one of them. So, and this is exactly what we will use later. Okay, now what about bisection? Can we apply it here? So we see that we can easily generalize fixed point iterations, right? Yes, condition for convergence is as impractical as before, even more impractical, but still we can generalize it. So it's essentially we can write our equation in this form and then just formulate the iteration process and then just hope that we will converge, right? So at least we can try it. Okay, so can we apply bisection in multi-dimensions? Hello, anybody?
I don't see a clear way to go from the bisection in one dimension to multiple, but
yeah. So the problem with that is that essentially we were using geometric approach, right? So we were just considering the function. So we were saying that, okay, let us consider this interval from A to B, right? And we were considering now again the problem like that, right? So a little bit different from fixed point iterations. And essentially we were saying, let me split the interval in half, right? So, and then I was essentially having a look at what part of this interval I have my zero here in this part of the interval, right? Then I was again splitting it in half, and then, okay, here we have, right, our zero, and so on and so on. The problem was that we were using continuity of a function, and we were just essentially checking for every interval, if interval from A to B, if this is less than zero. So essentially we were checking if our function is changing sign on the sides of the interval, right? Like here, like here. So the thing is that for multidimensional function, you don't have that simple condition. Although in your notes, it's written that there is no such result in multidimensional case. Really, there is similar result, but only for two-dimensional case. And really not two-dimensional case, but on the complex plane. It's called Lemire Schur algorithm. And it uses, you can use it only for some specific function, and it uses essentially complex variables theory of functions with complex variables, essentially a result that when you calculate in for so-called meromorphic functions, so you can find the number of zeros of your function inside of your contour, and then you can do the following. You essentially consider some search area, and then what you can do, you just split the search area into quadrants, let's say 4 quadrants, and then you compute the contour integral and find if there are zeros of your function in every quadrant. For example, you have zeros here and here, and no zeros here and here. So you found just number of zeros. So then correspondingly, you split each of these quadrants into 4 other quadrants and repeat the process. So, but this works only in complex plane, and you need to have a meromorphic function, so-called meromorphic function, which means that you need to have a function without singularities in this search area, and also the only singularities which you can have are poles, and so on and so on. So essentially, but there is no general approach for n-dimensional systems. So yes, you can, with very strong efforts, spending a lot of efforts, you can go a little bit further to the 2 dimensions. In some cases, it will work, but it's way harder than bisection in 1D, and not always it will work. And there is no way to continue this process to 3 dimensions. So this is why we just, okay, we are saying that, okay, bisection is great for 1D case or scalar case, but we cannot easily generalize it to 3-dimensional, even 3-dimensional case, and not talking about general n-dimensional case. Okay, then let me consider Newton's method. Let me remind you what was there. So Newton's method, essentially what we were doing, so we were getting these. It's the same as if I would divide it, right? So I just would like to write it like that. So, and how we were getting that? So we essentially were saying that let me consider f at the root plus some small epsilon. So small deviation. So then how you can write it? You can write it using just Taylor series, right? So you can write it like that. And epsilon plus and so on. So this is equal to 0 because r is the root, right? And let us neglect everything else further. And then we can get that this deviation epsilon is nothing else but negative f of r divided by f prime of r, right? And then we were saying, okay, how can we approximate the deviation from the root? We can say that, okay, let it be approximately xn distance between successive approximations, right? And instead of these, I would use the previous approximation, and then we are getting exactly +1 xn minus f of xn f prime xn. So we are getting this. Pay attention that essentially we were solving here. So this was essentially the following. So you can rewrite this as f prime of xn multiplied on xn plus 1 minus xn equals to negative f of xn, right? So just like that. Okay. So what we have in in the case of matrix approach. So we have the following. We can write that our f at the root, right, has to be a 0 vector. But now let us consider some point which is so let us try to perturb this root with the epsilon. Then how can we write it? We can write it like plus, and here if I will just write it, but derivation you can see in the so if you will take at least the calculus, calc 3, so there is this introduction of Taylor series for multivariable functions, and so further terms. Once again, we neglect further terms. Once again, these we replace. So yeah, so we are bringing this to here, this to here. This is again 0 vector, right, by the definition. So and this is what we do. So we essentially getting df. df, let me remind you, is nothing else but Jacobian, this matrix, right? And df multiplied, again, I will approximate my epsilon by xn plus 1 minus xn, just perturbation, so equals to, and here we have negative, so because this thing we are bringing to the right hand side, so here we have negative f at xn. Okay, so from here, pay attention, this is n by n matrix. This is n by 1 vector. And this is n by 1 vector again. So we can consider it as a system of linear equations with respect to these. We can find it, this difference, right? So for example, I can denote it as delta x. So, and then knowing that delta x is xn plus 1 minus xn, from here I can immediately get that my next approximation is nothing else but xn plus this delta x, right? So just, and I can update my approximation and then just repeat the process. Okay, or you can write all these as xn plus 1 minus xn equals to negative df inverse Jacobian matrix applied to f of xn, and then xn plus 1 is nothing else but xn minus inverse Jacobian matrix, which is nothing else but direct analog of this, right? Pay attention, I specifically have written it in this form. So once again, instead of division, right, because there is no division for matrices, we can introduce only inverse matrix, right? So this is what we have, okay. But formula is practically exactly the same, right? So instead of derivative, we have Jacobian matrix. So instead of these scalars, we have vectors, and instead of this, because we have vector function, we have vector again. So just this. So, but I want to tell you that once again, like we are not finding, like in the case of a system of linear equations, we are not trying to find inverse matrix, right? And then use it, right? So on the multiplied on the right hand side, because it's just inefficient. So what we are doing, we are solving system of linear equations, like here, here. Instead of that, we are just using LU factorization, right? And solving system of linear equations using backward and forward substitutions, right? Just remember what you have done before. Here, it's exactly the same, exactly the same. You are solve this. Not this. Because this is expensive. It's more expensive than LU factorization of that, and then solution for delta x, and then update like that. So believe me, it's more expensive. So you can try to read about different algorithms for finding inverse matrix, but usually they require you first perform LU factorization anyway, and then perform more operations. So in many cases, it's several times longer or several times more expensive computation-wise to get the inverse matrix and then to multiply it on the vector. So this is why I do not recommend this. Just get this matrix. So after that, you have your equation df computed at the previous approximation, right? Jacobian matrix multiplied on delta x equals to value of your function at the previous iteration, and delta x is nothing else but xn plus 1 minus xn. So solve this system of linear equations using LU factorization, and then after that your xn plus 1 will be just xn plus delta x. So Newton's method in n dimensions, right? So you see, Newton's method can be easily generalized. I mean, not that easy, of course. Instead of just derivative, now you need to compute the matrix, right? Jacobian matrix. So it's not so easy to generalize, but it's possible. And what is interesting here, we can use exactly the same approach as we did before to find the approximation of Jacobian matrix like we did. Okay, let me come back. Like we did here in secant method, we were using this approximation to find the derivative. So we will use something similar, not exactly the same, but something similar in order to find numerically the approximation of the Jacobian matrix. But for now, let me just give you the feeling of what we are doing. So essentially, let me write the following f1, f2, f3 of x, following system of nonlinear equations. So f1 is x1 cubed plus sine e to the power x2. Here, logarithm of x2, x3. Here we have x1 squared divided by x3 plus 4. Again, of course, we require this to be equal to the 0 vector, right? Okay, now let us find the Jacobian. So let me remind you that df ij is nothing else but dfi by dxj. Okay, now df matrix will be, okay, component 1, entry 1, 1 of the matrix, which means first row, first column. We need to compute partial derivative of df1 by dx1. Could you please tell me what it will be equal to? Essentially, partial derivative of that with respect to the x1.
Just 3x1 squared.
Right. df1 by dx1 is 3x1 squared. Pay attention. This is considered to be a constant because, as I said, for partial derivative, we freeze all other variables. Okay, so I know that my entry here is this. Okay, what will be df1 by dx2? So, or component 1, 2 of the Jacobian matrix, first row, second column. Okay, so it's composite function, right? Right? So we essentially first compute this. We'll get cosine of ex2. And now we need to multiply on the just chain rule, right? On the derivative of that with respect to x2, ex2, right? Just like that. Pay attention, once again, we consider this x1 cube as a constant, so this is why it gives us nothing. So, okay, ex2 cosine of ex2. Okay, what will be df1 by dx3?
Just 0.
Right, because there is no dependence on x3 here, right? Partial derivative is just 0. Okay, df2 by dx1. So this is my f2. Does it depend on x1 at all?
No, the
No.
partial derivatives will be 0.
0, right? Okay, df2 by dx2. Okay, so logarithm of x2 x3 can be represented as logarithm of x2 plus logarithm of x3, right? So can you compute the derivative with respect to x2 of this expression?
Just 1 over x2.
Right. And what about derivative with respect to x3? Oops.
Just 1 over x3.
Right. Okay, so now let us compute so this element is 3, 1, right? So df3 by dx1, what it will be equal to. So this is f3, df3 by dx1.
2x1.
Not exactly. So what about the denominator?
One half x1.
Yep, 2x1, right? But don't forget denominator, which you now consider just as a constant, right? Because you're computing partial derivative. Okay, what about df3 by dx2? Do we have any dependence on x2 here?
It should be 0.
Right, because there is no dependence, it's just 0. Now, what about derivative with respect to x3? df3 by dx3, partial derivative. So df3 by dx3. So first of all, it's 1 over x3. So once again, remember, this stays as a constant, right? So, and you have 1 over x3 plus 4, right? You're computing derivative only with respect to x3. So it's power negative 1, right? Divided by x3 plus 4 squared, right? Just this. So we are getting negative x1 squared divided by x3 plus 4 squared. Just this. Is it clear or not? How to compute the Jacobian?
I think it's clear.
Okay, so you see, even for three-dimensional system, so it took us some time, right, to compute this. You can easily imagine that, for example, if it's 10-dimensional system, right, and believe me, there are systems which are 1,000-dimensional and so on, and these are practical applications, what I'm discussing. So in such a case, your Jacobian matrix will be, for example, if even for 10 by 10 system, it's just 10 by 10 matrix, it's practically, I mean, it's not practical to compute it. Even if you have f of x represented through analytically like that, which is also not usually the case. Usually you just have some algorithm how to compute your function if you know x1, x2, and so on. It also can be numerical approximation. So as a result, in many cases, this is impractical. So the analytic computation of the Jacobian matrix. Okay, so then there is, of course, approach similar to secant method. So let us remember what is df, for example, df1 by dx2, partial derivative. It's the limit delta x2 goes to 0, f1 of x1, x2 plus delta x2, x3, xn minus f1 of x1, x2, x3, xn divided by delta x2. So essentially exactly the same as derivative before, right? So for a function of one variable, just now we are perturbing just one derivative x2, right? So, and obviously for x3 it will be the same, just you perturbing just x3 and so on and so on. Okay, so we can try to, of course, do the following. We can say that, okay, df1 by dx2, we can say that it's approximately equal to f1 x1 x2 plus delta x2 and minus f of x1 x2 xn divided by delta x2 for sufficiently small delta x2, right? So if we choose it small enough, so we can say that, okay, most probably it will be good approximation to the derivative. We will study how to control this error and what it will be using different methods. So, but for now, let us consider just the simplest case, just going exactly from the definition, just replacing these infinitely small perturbations, infinitely small, pay attention. So we are just replacing them with finite perturbations. Then this is what we do. For example, we can just consider, so if we want to compute df Jacobian matrix J kth element, so what it will be? It will be dfk df. Okay, let me use the same notations so that you will you will not get lost. Ij dfi by dxj, right? Like that. So then what I can do, I can say that, okay, I can approximate it using this formula, just fi x1 xj plus delta. Okay, let me call this, use the finite delta like that, right? Xn minus fi x1 xj xn divided by this delta, right? And if delta is small enough, so sufficiently small, so then I hope that this will be a good approximation, right? So the result, you can say how you can write these. You can write these as, if you have vector x, you can write it as delta multiplied on EJ, where EJ is the basis vector from the natural basis for the n-dimensional space, which is nothing else, so don't be scared. So in jth position. So essentially you take 0 vector and put 1 in jth position. So for example, for 3 by 3, for three-dimensional case, this is our natural basis, right? So called E3. So, and this is our E1, E2, E3. So how to do this? So you just create 0 vector using, for example, in MATLAB using zeros, zero separation, and then replace jth entry with 1, just assign 1 to the jth entry, and then you just multiply this vector by delta. Okay, and then have a look what it will give you. So it will be x1, xj minus 1, xj, xj plus 1, xn plus 0, 0, delta, 0, 0. So this goes to here, this goes to here, this goes to here, this goes to here, this goes to here. So the result, it will be nothing else but x1, xj minus 1, xj plus delta, xj plus 1, xn. So nothing else but exactly the vector for which you need to compute your function in here, right? So then, essentially, in order to compute d f I by dx j at the vector x, right? So you approximate it with the gij, which is fi computed at x plus delta ej minus f of x divided by delta. So, and then you compute it essentially. So ij, they take values 1, 2, and so on till n. And then you will compute all. So this will be nothing else but all entries of Jacobian matrix. So delta is sufficiently small. Say, pay attention, I'm just saying. So 10 to the negative 2 or 10 to the negative 3 or something else. So idea is that you can, for example, try to compute these Jacobian for different deltas, right? And then subtract these two matrices and see how they difference, if they difference, the norm of their difference, L infinity norm, for example, is less than some required. But for now, we can just say that, okay, let us just do it like that. So we just fix some delta small enough and get in this. So we can get matrix G, whose ijth element is the corresponding Gij computed like using this formula. So then, what we are getting? So this is approximation of Jacobian matrix. So essentially, we have G computed at the xn vector. So where xn, n is nth iteration, so multiplied on I'm just showing you where it's coming from. Here we found approximation of this Jacobian using this numerical approach. So we found this matrix G. So now we can just apply these just like that. Like, so pay attention that this is approximation of Jacobian. So this is system of linear equations. So just what you do, you use LU factorization here. So you have all the methods. Then you solve the system of linear equations. You know that this is nothing else but xn plus 1 minus xn. And after that, you essentially solve for delta x. And then your xn plus 1 from the definition of delta x will be nothing else but xn plus delta x. That's it. So, and this is Newton's approach in multi-dimensions. So of course you can write it xn plus 1 equals to xn minus g inverse f of xn. For example, you can just use this function in MATLAB like a division, right? So just in different, I mean, with the inverse slash, backward slash. So, but the right approach, the more efficient approach is just to solve this system of linear equations using LU factorization. So, okay, so this is how you do this. This is the approach, and this is essentially multidimensional Newton's method, which is called Newton's Raphson method, or Raphson's method.